Hi, I'm Wallace Kelly, and now it's time to look at some examples from Book 3 of propositions regarding circles. We want to be able to explain what a proposition says, but also organize its proof into a proof table, and along the way jump into our geometry software and experiment with what we're finding. Recall that a circle was defined in Book 1, Definition 15, and it said that a circle is a plane figure contained by one line such that all the straight lines falling upon it from one point among those lying within the figure, such that all the straight lines going through that one special point equal one another. And that's what defines a circle. Proposition 1 is a construction proof. It shows how to find the center of a given circle. That is, if you already have a circle and you don't have any indication of what the center is, there's a pretty clever way to find it. Here is an example implementation of Book 3, Proposition 1. We have a circle, but we don't know where the center is. What you can do is draw a line through the circle at random points, and then bisect that line, and then identify where a perpendicular line intersects the circle, and then bisect the line between those 2 points. In this diagram, F is at the center of the circle. Let's jump ahead to Proposition 3. If in a circle, a straight line through the center bisects a straight line not through the center, it also cuts it at right angles. And if it cuts it at right angles, it also bisects it. These are really two different propositions. One is the inverse of the other. Here's a detailed description. It says, let a straight line CD passing through the center of a circle, ABC, bisect a straight line AB, not passing through the center, but bisecting it at point F. You can see that it's bisecting here because both sides are of equal length. The conclusion is that it cuts it at right angle, or that this angle in here should be 90 degrees. Here's that same diagram, except this one's dynamic. Notice that right now, each side of this line has length 3, and we have a 90-degree angle. But if that angle goes off of 90 degrees, notice that the lengths on each side are not equal anymore. It's not being bisected. However, if I move this around until I get about a 90-degree angle, or as close as I can get with a mouse, these two sides are now going to be equal, and that line is being bisected. That's the only way to bisect another line that doesn't go through the center, is if it meets it at a 90-degree angle. The proof begins by saying, take the center E of the circle ABC. Book 3, Proposition 1, showed us how to find the center of a circle. Next it says, join EA and EB. We know how to do that from Book 1, Postulate 1. You can probably see where Euclid is going with this because we have two triangles here that have a common side. Next, the proof says, then, since AF equals FB, how do we know that AF is equal to FB? Well, actually, that was part of the problem statement. It said that if a line CD bisects a line AB. So that's a given. Next it says, notice that FE is common. And again, here you can see that Euclid is building up two triangles. FE is common to those two triangles. We might say that FE and EF coincide, which is a reflective property. Maybe we could put Book 1, Common Notion 4 to indicate that that's a reasonable thing to assume. The next thing is to say that notice that two sides equal two sides. we've already identified that AF and FB are equal to each other, and then we see that FE is common. So we have two sides equal to two sides, and we also see that the base EA equals the base EB. How do we know that EA is equal to EB? Well, because E is at the center, A and B are on the circumference of this circle, and so by the definition of a circle, those two lines are going to be equal to each other. The next phrase says, therefore, the angle AFE equals the angle BFE. Let's see, AFE, that would be this angle, equals BFE, that would be this angle. And how do we know that? We've just shown that in these two triangles, all three sides are the same. So we have the side congruency, which in Euclid's Elements is Book 1, Proposition 8. Therefore, we can conclude that these angles inside, the corresponding angles inside, are equal. Next, the text of the proof says, but when a straight line standing on another straight line makes the adjacent angles equal to one another, each of the equal angles is right. Therefore, each of the angles AFE and BFE is right. That's a reference to Book 1, Definition 10, where we found that if we have one line standing on another line and the angles on each side are equal, then they must be right angles. And that was the point of Book 3, Proposition 3, at least the first half. The second half deals with the inverse, that if these two lines intersect and form a 90-degree angle, then line CD bisects AB and the two segments on each side are equal. Another interesting proposition from Book 3 is Proposition 20. In a circle, the angle at the center is double the angle at the circumference when the angles have the same circumference as a base. Let's look to see a little bit more detail what this is talking about. Let ABC be a circle. Let the angle BEC, that would be this angle right here, be an angle at its center, and the angle BAC, this angle out here, be an angle at the circumference. And let them have the same circumference BC as a base. They both have endpoints at the endpoint of this arc. Euclid says that the angle BEC, the one in the center, is double the angle BEC on the outside. Here we have that same proposition in GeoGebra. Notice that there is an angle beta at the center of the circle and an angle alpha on the circumference of the circle. And both of the angles span the same arc B to C. Over on the right, you can see that alpha is 1/2 of beta. And that relationship is maintained even as we adjust the size of this arc or move the outer angle around all along the circumference. It's a pretty remarkable result. Let's look at the details of the proof. First, the text says, join AE. That's already been done in this diagram. And we know we can do that from Book 1, Postulate 1. Then it says, and draw it through to F. This is actually an application of Book 1, Postulate 2, where we can extend an existing line. Next, the text reads, then, since EA equals EB, since EA equals EB, and how do we know that? Because E is the center of the circle and A and B are on the circumference, so by definition they are going to be equal length. The angle EAB also equals the angle EBA. EAB, this angle here, equals EBA. How do we know that that's true? Well, this is an isosceles triangle, and Book 1, Postulate 5, told us that the angle inside, and actually on the outside if we extend these lines, is those two angles are equal. Then it reads, Therefore, the sum of the angles EAB and EBA is double the angle EAB. Basically, what we're saying is that if we add these two angles on each side, which we know are the same, then that would be equal to 2 times one of them. The text continues, but the angle BEF, this angle here, equals the sum of the angles EAB and EBA. How do we know that? If we reach back again into our memory, we'll remember that Book 1, Proposition 32, said that if you have a triangle and you extend one side of it, the exterior angle will be equal to the sum of the interior and opposite angles. And that's what's being applied here. Keep in mind the big picture. We're wanting to show that this angle BEC is twice the angle BAC. And so far we're halfway there, because working on this triangle EAB, we've shown that this angle EAB is equal to half of BEF. Or as the text says, therefore the angle BEF is also double the angle EAB. Now we turn our attention to the other half of this problem, the triangle AEC. For the same reason, the angle FEC is also double the angle EAC. What would be the details of that? Well, first, we would need to show that EA is equal to EC, and that's by the definition of a circle. E is at the center, A and C are on the circumference. Angle EAC is equal to ECA, so this angle here at A and this angle here at C are equal. And again, that's Book 1, Proposition 5, the angles in an isosceles triangle. And then finally, because the two angles in these corners are equal, the sum of those two angles is equal to twice one of them. That's important because the next step says, or the next step would require that angle FEC, again this one, is equal to the sum of these two. And again, it's the same thing where we have a triangle and we extend one side, and so this angle inside on the outside of the triangle is equal to the sum of the interior and opposite angles. So then we can conclude that FEC is 2 times this angle EAC. So we could mention explicitly that BAC, this angle here, is the sum of the two inside it, and then this angle out here, BEC, is the sum of the two angles inside it. And having shown that BEF is twice BAE, and having shown that FEC is twice EAC, then we can conclude that the whole angle is twice or double the whole angle BAC. Let's just quickly look at one more, Proposition 21. In a circle, the angles in the same segment are equal to one another. Here's the detailed description. Let ABCD be a circle, and let the angles BAD, that would be this one here, BED, that would be this one here, be angles in the same segment. This time, the segment goes around the outside. I say that the angles BAD and BED are equal to one another. Let's check it out in GeoGebra. Notice that as I move these points around, those two angles remain exactly the same, regardless of the size of the segment or how the points A and E are positioned in that segment. That's another very impressive conclusion. We just finished looking at several of the propositions in Book 3 related to circles. We also took 2 of the proofs and translated them into proof tables to make sure that we could understand the logic. It's helpful as you're doing this to open up your geometry software, construct what is being described in these propositions, and see for yourself how these work dynamically.